So yesterday, right, we approached this problem of calculating the area under a curve and above the x-axis between x equals a and x equals b, okay, on the x-axis. And we said that we could approximate that area using rectangles. Okay. And the more rectangles we use, right, the better our approximation to the area under the curve and above the x-axis. And that sum that we use, right, the sum of the areas of the rectangles, right, is called a Riemann sum, named after this guy right here, right? He was 39 years old when he passed away. Okay, so he accomplished a lot in the 39 years he was on this earth. All right, and so for the cubing function, right, over the interval from 0 to 6, right, we calculated the Riemann sum for that function over that interval, right, using left endpoints and right endpoints. And at the bottom of page 4, okay, we made this little table, right, based upon the number of rectangles, right, whether we use left endpoint or right endpoints. And right, we noticed that the more rectangles we use, right, the better our estimate was for the area under the cubing function and above the x-axis from x equals 0 to x equals 6. And we had made the point, right, that when the number of rectangles, right, increases without bound, okay, then the left endpoint method and the right endpoint method will both give you the exact area. Okay. So in fancy mathematical notation, we should write, okay, so remember, our area is approximated, right, with the Riemann sum. And so the exact area can be written as, okay, the limit as n increases without bound, okay, of the Riemann sum. Now I'm going to use what's called sigma notation or sum notation. I'm assuming you've seen this in high school, okay? The sum from I equals 1 to n, okay? The Riemann sum, right? Products of f of x sub I star times delta x. So remember, this is the area, fx sub I star times delta x is the area of the ith rectangle, okay? Delta x is the width, and f of x sub I star is the height. Okay? And so if we increase the number, n is the number of rectangles, if we increase the number of rectangles without n, okay, then the limit of this sum, right, gives us the area under the curve and above the x-axis over the interval of interest. Any questions on that? Okay. All right. So if you flip over your handout, we're going to look at what is called the distance problem. And the distance, solving the so-called distance problem is identical to estimating the area under the curve and above the x-axis using rectangles. Okay. So we're going to demonstrate that with an example. This is where you sort of got to use your imagination. Okay? So we have a runner, and at intervals of 10 seconds, we can measure their velocity. but we don't know how far they run for whatever reason. Okay, so this is sort of a, right, this is from mathematical, teaching the concept, okay? I mean, in practice, you should be able to measure how far they ran in 10 seconds. So we're using, right, velocities, right, recorded velocity at 10-second intervals, and we're going to use that to estimate how far the distance traveled in 60 seconds, okay? So I can remember studying what is called uniform motion in high school. Now maybe they call it something else these days, okay? But it's rate, uniform motion is rate times time is equal to distance. Okay. Do you remember? Did you ever hear that phrase? Rate times time equals distance. Okay. And the rate, right, is just another word for velocity. And this formula works if velocity is constant over a period of time, right? So you could really write constant velocity times time is equal to distance. If velocity varies, okay, then this doesn't work. Okay? This only works for constant velocity, constant rate. So this formula, right, velocity times time equals distance, looks a lot like width times height is equal to area. The area of a rectangle. Okay? And so calculating distance, right, is kind of like calculating the area of a rectangle. Okay? It's just a product of two quantities. So if we graph velocity versus time, right, in the coordinate plane, so t, right, is time, v is velocity, and time is recorded in 10-second intervals. And now we'll plot the velocity, okay? So here's what, 5, 10, 15, 20. So this is just an approximation, okay? So at the beginning, at time 0, the velocity is 0, right? So that's the origin. At time 10, the velocity is 6. So this is 5, 10, 15, 20. And so at t equals 10, the velocity is 6. At t equals 20, the velocity is 11. At t equals 30, the velocity is 15. At t equals 40, the velocity is 18. At t equals 50, it's 19. And t equals 60, it's 20. So that's the plotting, right, of the velocities. I'm standing up here at the board, right? It's hard to see if I'm getting what I'm doing plotting this. Right, but you get the idea, okay? Then you can see, right, the runner's, right, speed is not increasing very much, right, after about 40 seconds. Increases quite rapidly at the beginning, okay? And then it levels off. So if we just kind of play connect the dots for a second. Okay, just imagine. So here in yellow, kind of connecting the dots. And so that might be the velocity function. Okay. Now we only have these 7 data, right? 7 data points. But you know, with tech index, you know, that kind of looks like the velocity function, right? It's a function of time. And so in estimating how far the runner ran in 60 seconds, right? It's time times velocity equals distance, right? So we can estimate the distance over the first 10 seconds, then the next 10 seconds, and the next 10 seconds by drawing rectangles. Okay. And the area of those rectangles, right, is our estimate of the distance of how far the runner ran in those 60 seconds. So we can calculate a Riemann sum, right? Using left endpoints, using right endpoints. So delta t in this, right, instead of using delta x, right, we're using delta t. Our delta t is 10 seconds. Okay. So we can create a table like we did yesterday for our rectangles. And, right, so the base of each rectangle, we're going to have 6 rectangles. The base of each rectangle is 10 units, 10 seconds wide. Okay. And so the first one, right, goes from t equals 0 to 10. The second one goes from 10 to 20. The next one from 20 to 30. The next one from 30 to 40. The next one from 40 to 50. And the last one from 50 to 60. So if we use the left endpoint method, okay, I put x. That should be t. Okay. So for the first one, right, the left endpoint method, we use t equals 0. For the next one, t equals 10, then 20, then 30, then 40, then 50. Then we put the corresponding velocity at each of those times. So at t equals 0, velocity is 0. At t equals 10, velocity is 6. At t equals 20, it's 11. At t equals 30, 15. At t equals 40, 18. And at t equals 50, 19. So this is the times and the velocities, right, doing the left endpoint method with 6 rectangles. Now in the same table, I'm going to include the right endpoint numbers. Okay. So using the right endpoint of each interval, t is equal to 10, 20, 30, 40, 50, 60. And then the corresponding velocity. T equals 10, the velocity is what, 6? 6, yeah. 6, 20, t equals 20, it's 11. We have 15, we have 18, we have 19, and then we have 20. So our estimate for the distance that the runner ran using the left endpoint method, okay. Remember, each of these velocities get multiplied by delta t, which is 10. Okay. So we can just add up the velocities, 0 plus 6 plus 11 plus 15 plus 18 plus 19, okay? And then multiply all that by delta t, which is 10. Okay? So each of these velocities times delta t, right, is an estimate of the distance the runner ran in that time interval. Okay? And when you add up all the velocities, okay, and then multiply them by 10, I get 690 feet. So 0 times 10 is our estimate of how far the runner ran in the first 10 seconds, which is 0 feet. 6 times 10 is our estimate of how far the runner ran in the second time interval, and so forth. And so, since our velocity function is increasing, right, from left to right, this is an underestimate. All these rectangles, right, are going to be under our curve. Okay, they're not going to contain it. And then R6, the right endpoint method, right, the right endpoint Riemann sum. Okay, so we take all these velocities, right, add them up, and multiply by delta t, which is 10 seconds. So we have 6 plus 11 plus 15 plus 18 plus 19 plus 20 times delta t, okay, which is 10 seconds. And when you do that arithmetic, you got 890 feet. That's an overestimate, okay, of how far the runner ran. Okay. Because when you draw those rectangles, right, it'll contain all those rectangles will contain all this area. Okay. So we're only given velocity at discrete points, right? But what I drew in yellow, we could imagine as the velocity function. It's a function of time. Okay. And so with uniform or velocity varying, right? Velocity changing over time, okay? We can estimate how far a runner ran, right? Just like we estimate the area under a curve. It all kind of boils down to rectangles, right? Constant velocity times time equals distance, right? Is a lot like width times height times area as a formula. Okay. Any questions on that? Okay. All right. And so just a reminder, okay, homework 5.1 is due at the beginning of class.
So like this question saying estimate the distance, we would still give you both, like on the left and right?
Yeah, I mean if it asks for that, yeah. If only asked for the right, then you would only get
But
the
you
right.
would like explicitly say.
Whatever the instructions are. Okay, follow the instructions. All right. So all this discussion about area under a curve, estimate area under a curve, leads us to the definition of the definite integral. Yeah. So if you give Sahar one, Sahar will give you it. Now this packet looks big, but like the first 3 pages, okay? We're just talking about what the definite integral is, right? Properties of the definite integral. Okay. All right. So first 3 pages are foundational.